Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks with Washington University. This is Module 12, Deep Learning for Information Assurance and Security. Part 1 is just a general overview of security for deep neural networks. There's a wide variety of ways and aspects of security in general. The area that I know the most about is intrusion detection systems. I worked on this, some research with my PhD advisor originally, and have kept a little bit up to date on this area. This is definitely an area that deep neural networks are being applied to, and it's an area that I will talk some about in this presentation for this module. I'll also show you the paper that I was a part of the publication on in this specific area that we presented at MILCOM in 2017, which is a U.S. military conference. So security data can be very, very complex, and an intrusion detection system will deal with data like this. You'll have wired and wireless PCAP files, you'll have web server logs, you have operating system event logs, and then you'll have other data types as well. You can take these all through a traditional manual threat assessment and generate targets. So you're taking samples of all of this data and assessing it as threat or no threat. And this data, by doing this gives you your X and your Y that you can fit a deep neural network to. Now there's other ways to do this, but this is the way. If you have a lot of data that you have classified as threat or not threat, if you don't have such a data source, you need to consider other options like creating an anomaly detection system or perhaps something else. The paper that I was a part of, some research that we did and presented at MILCOM, was to create a prototype for attack triage and prioritization. This is using an intrusion detection system. We use Google TensorFlow, and we had a paper for the 2017 MILCOM. So that's a small typo there. We trained it using TensorFlow with a GPU. Predictions, we used predictions with the CPU, mainly because the training was the really, really slow part. So we just needed the GPU for the training of the neural network. This is what the FASTT system looks like. It's a triaging system. So it's meant to essentially take the very, very large amount of data that's coming in on one of these systems and basically triage it and prioritize it. So take the threats that look high importance to send those off to human analysts so that they can check them out and perform their threat assessment. And the human analysts are very much an important part of this, and they are how we generate the actual training data for it. So I'll get to that slide in a moment, but the paper that we presented shows largely where I got some of the individual images from. This paper was done by myself and a number of other people, Stephen McElwee, me, James Fraley, and James Kennedy. You can basically pull this up in Google Scholar if you have the appropriate accesses for that. That's the diagram that I really just showed you. And we created a relatively shallow neural network. We did not require a tremendous amount of hidden layers to do this. And we were able to essentially set up the data pipeline so that we were able to visualize the data with Kibana. It was very important to be able to see the data and look at it as it's coming in, and create the deep neural network classifier to assess this as threat or no threat. That's what the visualization of this looked like as we made these classifications sort of in real time. And the results, we got a very good 98% classification accuracy on the data set that we were actually looking at. Now, looking at security data or any other sort of data, it's very, very tricky because you have to consider a lot of different things. You have to consider, are the data coming in representative of your real data? So for example, most network transactions are not any sort of a threat. So you're going to have this tremendous sea of data where you have no threat and a few little threats sprinkled throughout that. That's very fortunate for security of computer systems, but very unfortunate for training the deep neural network. You also have to make sure that the data are representative. So say you are trying to create and you have to be careful of target leakage. That's where you're conveying information about the target that won't be available at train time. So here, maybe we're trying to create a classification network that can tell the difference between cars and trucks. Do you see anything inherently wrong with this data set? The problem is all the cars are gray and all the trucks are blue. And the neural networks are much better at detecting wide swaths of color. So this would basically, if you trained it on this, you would create a blue detector, which is probably not what you were going for. This is an image that's been passed around the internet a lot, showing how you can confound neural networks. And I don't think I'll ever look at a blueberry muffin the same again, but is it a dog or is it a muffin? And you can see how remarkably similar the two things look when put side by side, Chihuahuas and blueberry muffins. I really do like blueberry muffins, and I like Chihuahuas okay. I just don't like to eat them. This is another area, potentially, though, for security that you want to be aware of. Is it a stop sign or is it not a stop sign? These simple defacements, and I show the paper there, show that it's possible to cause the computer vision to not recognize this as a stop sign. This is a real problem for a self-driving car, and something that will definitely need to be addressed. This is another example of how you need to be careful with classification. If you're trying to tell the difference between a wolf or a husky, make sure that the pictures that you take don't have some other feature in it that's more predominant. Now, wolves and huskies do look pretty similar, but can you see any issue with these images? All of the huskies, all of the wolves are on snow, mainly because they're not, you usually don't have wolves sitting in people's yards. Whereas the huskies are all sitting on yards in almost suburban type surroundings. So this program had essentially created a snow detector. This is where there is a type of analysis that you can do where you ask the neural network to really show you what part of the image it's using, what is the most important part of the image. And you can see it doesn't even care about the dog, it cares about the snow. It's basically a snow detector. There's been quite a bit of mention of this particular training as sort of a failure of neural networks, and in particular a failure of finding the proper sets that you want to train it with. This paper, you can look it up, is very interesting. It was not released that long ago. It shows how you can do a 1-pixel attack for fooling deep neural networks. And this is a big area for security research. How do we secure these machine learning models so that people don't try to game the system and exploit the neural network? Here you can see that in this paper, what they did is they used machine learning to try to figure out how to fool machine learning. So here you have something that should be classified as an airplane, and the neural network would have classified it as an airplane. Unfortunately, that little green pixel was added that the machine learning figured out, and now it's a dog. here's the another case of an automobile becoming a dog. Just that one little pixel. That really shows you how complex what is going on under the hood with the neural network. Who knows why that little pixel just unravels the entire thing and causes the neural network to incorrectly predict. And you can see other cases where this horse now becomes an automobile. The dog becomes a horse. And so on. Just a lot of things that you have to be aware of. Now for security, if you're doing an intrusion detection system, you need to be careful of the fact that people may use machine learning to figure out how to mess with the data in such a way so that the attack becomes invisible or is misclassified. So the one pixel attack is a very recent paper and very important for looking at how neural networks and other machine learning types can be potentially easily exploited if the right way to fuzzify the data is discovered. You also have to be aware of correlation versus causation. And I have a few extra videos that you can look at here if you find this interesting. They look at basically, does ice cream cause drowning? Well, if you Google this on YouTube, there is quite a bit of public service videos urging people to not allow their children to eat ice cream because it might cause polio. Now, it doesn't cause polio or drowning, but if you look at a chart for ice cream versus drowning, ice cream versus polio, ice cream consumption goes up radically in the summer. So does drowning. So does polio. Polio goes up in the summer just due to the biological nature of the disease. Drowning goes up in the summer just because people are swimming more, so they're more likely to drown. So you need to be aware of what's called spurious correlations, and there's a number of these. Where the charts, if you look at them, it kind of makes sense. Maybe Nicolas Cage appearing in films actually causes drowning. If you look at those two charts, there does seem to be some correlation. Obviously, there's nothing. This is from a site called Spurious Correlations that just went through a whole bunch of data and tried to find ranges where certain things appeared to correlate. This one might be believable. Actually, I'm kidding, but computer science doctorates awarded in the United States versus the money generated by arcades. There might be some explanation for this, but this shows that the two look relatively connected. Now, if you know that clearly two things are not connected, this will seem silly and you'll discard it immediately. But if you're dealing with data that you're not that familiar with, like maybe the number of telnet sessions at 8 a.m. might be indicative of if a noon attack will happen or something such as that. That might seem reasonable if you're not as familiar with the data. We are going to also look in this module at something called the KDD-99 Dataset. This has almost become the hello world of intrusion detection or security data. It was a competition put out by ACM back in 1999. And we'll see this data set. It's still often used as an example of security data even today. The next part in this module will actually take a look at how to use KDD data with TensorFlow. So the KDD data set, KDD, first of all, means Knowledge Discovery in Databases. This is a yearly conference put on by ACM. KDD is kind of what data science was before it was called data science. I guess before that it was called statistics. I don't know, but it's a new and evolving term. Data mining is another common term for this. It's a nicely formatted CSV. It's 750 megabytes, which is pretty big by 1999 standards, and it's a very common data set to look at for security. So we'll take a look at it in this module. These are the columns. These are pretty much data like might be coming off of a router: duration, protocol type, service, various flags, all of this, and then an outcome at the very end. The outcome is basically what sort of attack this was determined to be, or none at all, which is just normal. So these are all values that we have on these rows to just give us more information to help us hopefully determine the outcome. The most common outcomes in KDD-99, these are really a variety of these. There's also normal, which is what most of them are. There's all these other attack types that are encoded into this data set that let you know that that transaction was actually an attack. And by the way, this is a plot that I did of these. We'll see how to do this sort of. We've seen how to do this sort of thing before with feature importance. This is just feature importance. You can see that the number of bytes coming in on the source is very important, as are the destination bytes. The service type, like is this HTTP or something else such as this. So you can see there's a lot of features. They're not all as important as each other. This is another data set that is fairly interesting as far as security is concerned. So this is the malware classification. This was essentially a Kaggle competition worth $16,000, sponsored by Microsoft. This Kaggle competition asks you to try to classify malware. Now the malware, they do give you real malware. They're encoded in a non-executable form, but you need to analyze those and determine if they are malware or not. The data that you get for this the data are pretty large, 17 gigabytes. So what you'll get for each one of these, this is the tag, the transaction ID or the row ID. They give you the assembly language, so the decompiled assembly language, and then they give you the raw binary form of it, and just over and over. So it's those two pairs. These are two different files that we're analyzing. And then the winning entry, the team name was No to Overfitting, and you can see they're PhD students at the University of Pittsburgh, and then a data scientist. This is what the Kaggle leaderboard looks like for this competition. And this was the technique that they used. So remember we talked about essentially ensembling. So this was basically three models ensembled, a variety of models actually ensembled together. And they used XGBoost, they used other ensembles, and they also used semi-supervised learning. The feature engineering, they used n-grams for the assembly, which is basically just sort of word pairings or words in an order. Instruction counts, the function names, and then the assembly names. The golden features, now some of these are a little more complicated to explain than we'll get into, but what they mean by golden are these are the ones that they felt really won the competition for them. So the bottom one was very interesting. They turned the assembly into basically a pixel image, which allowed them to attempt to recognize that using image processing. Also, the opcode counts, so looking at the binary data and producing 2 grams, 3 grams, and 4 grams. So those would be just counts of 2 bytes that normally occur together, or 3 or 4. Just finding common instruction sequences was probably indicative somehow of if this was a malware or not. And this shows you how they converted the assembly image basically into an image. And this is what their images looked like. And they were able to do some computer vision on that. So I find that interesting. You've seen stuff like this. This usually happens when computers mess up and sort of memory gets flooded into the video range. This is the hardware that they used. They used Google Compute Engine, 16 CPUs. They did not make use of GPUs that I could determine, and they used a variety of packages, some of which we have experimented with here. Okay, this is the end of this part. The next part, we will see how to actually use some code and work with the KDD-99 dataset and try to predict it with TensorFlow.